always the case.
He's going for a week. For a week, and then another person from India is also going for 2 weeks. So I need to find 3 weeks. And like custom made.
Okay, if I open the windows, Martin?
Do you want to turn it to the fire? Because there's only one other and we can do like half and half.
Let me see where I'm standing. No, it's full. I don't need to show. Oh, that's full. Yes. Let me just.
Oh, sorry. Not that tiny.
And the other glass that you have now on your.
Or the glass art cell. This is one of the best actually.
Which you have art theory or art history?
Art history in the
Art history.
like 19th and 20th century. She's already got
Wow.
Peter.
Okay. So we're all good with the mic, I think. Should be okay. If not, what can you do? So,
Is the date, can,
sorry?
I didn't check that, but is the date of the exam available on Moodle already?
In Moodle, I'm not sure. It is in the
In the catalog?
in the annual catalog, I think. I actually need to check it because I'm really not sure when was. Do you remember when was the supposed date? No. I need to check it. I will. Right. Let me turn this on. All right. So I will say a couple of words. So next week, today we'll start the MVPA. Next week we'll continue with that, move to RSA a bit. Week after that, I'm not here, so there won't be any class.
Again. In 2 weeks, no class.
In 2 weeks, no class.
Okay.
In 3 weeks, this will be the last class, I think. 3 weeks from now. So in total, we have this week, next week, and in 3 weeks. And we want the class we miss. What we'll do instead is just a visit in the MRI facility. For those of you who want, I'll post some possible dates, and we'll do that somewhere in the last 2 weeks of June, I guess. Regarding the exam, Peter is right. I should at least check for myself. I'm not sure when it's supposed to be. We're not going to have an exercise. We thought about having some exercise, but it's just, I think we won't do it. And I'll cover more about the exam, okay, in the last class we have. I'll tell you exactly which papers are in, which papers are not, what is included. But on general note, like everything is included, of course. We want to ask you about technical details of papers, right? The idea is to understand the concept and to be able to think if we present some, I mean Udi and myself, if we present some logical question or some case study, to be able to understand the principles that you've learned here and apply it maybe to the case. So don't worry about the specific details. Okay, so today I'm going to switch gear into MVPA, which some of you know a bit about, some of you less. And before I do that, though, I want to spend like 10-15 minutes a bit more about statistics. So last time we covered the GLM, then we went on to the visual system and started to work our way describing the functional organization in the visual system, right? After, in the first, let's say, third of the course, we covered more the basic principles like eccentricities and location and such. we moved to define functional organization, and we talked about how we define the region of interest, the classical region of interest, how we can use this region of interest to ask specific questions, how we should define and how we shouldn't define a region of interest, and how to, in general, deal with data in a non-circular way. So before we go into MVPA, which extends everything we learned so far, just a few words again about the statistic, and this is, we're talking about univariate statistics, but basically it's the same for not only in fMRI experiments even, so something very general. So maybe you know this paper. There was, let's go over it briefly. There was stimulus that was presented in block design, okay, for 10 seconds each, and then 10 seconds of rest, 12 seconds of rest. So it's a block design experiment. And then they used SPM, doesn't matter. But they extracted the data, okay, did some pre-processing, co-registration. Then they ran GLM, okay, ran all the filters that we talked about. And, well, some other details. So they have interesting results. The only interesting thing about this experiment, that the subject of the experiment was one dead salmon fish. Okay, I don't know if you heard about this. And they found, so it's actually nice to read, right? So the task administrated to the salmon involved completing an open-ended mentalizing task. They had a very nice funny paper about it. So, but the idea is this, all right? They published these results, and they performed the normal pipeline we perform when we do the pre-processing, build the GLM and such, and discovered some active voxels in the mental visual imagery here in the dead salmon, which is, of course, a very interesting finding. Was it true? And the idea, of course, was to bring the spotlight of attention of the scientific community about the do's and don'ts that you should do when applying statistics, and specifically multiple comparisons problem. And we have very serious multiple comparison problem in MRI. We basically we have a t-test, and we try to see if a voxel is significantly active in one condition towards the other. And we have a lot of voxels, and sometimes we have multiple comparisons that we do within each voxels. So the problem is very large. And I'm not going to dive deep into that, but I just want to state really in a couple of minutes the approaches people use, each with its own pros and cons, okay? But just to get the gist of what we're talking about, so when you do a significancy test and statistic, you have a null hypothesis, and you have four results you can get. Okay, one is a hit, that something is significant. When it is significant, you can correctly reject the null hypothesis, or you can have type 1 and type 2 error. Okay, so one of them is that the region is not active, but it is detected as active or as significant, and the other one is the other way around, right? It's more conservative. We don't report an active voxel, let's say, in our case, but it is in fact active, so we miss something, all right? So these are the two errors, and the idea is, well, hopefully you would do the statistic correctly and do it in a way that will minimize both errors, right? You want to basically your results only be here, right, in these two quadrants. And the first more simple or more straightforward thing you do in statistics, and again, this is not only a functional MRI, is do a family-wise error, which is, in this case, the most familiar one is the Bonferroni correction, and then the idea is you just divide the p-value, that means significance, by the number of comparisons you do. Okay, so it's very straightforward. So if p-value is 0.05, you divide it by n, and that is the alpha rate that you have to be beneath it to reject the null hypothesis. Okay, so problem is with this system is it's very, very, very conservative. Okay? Let me forward this. All right. So the idea is, again, is to determine where, for a given voxel in our case, if there's a significant difference between conditions. And why do I say it's very, very conservative? Because it depends on the number of voxels we have. And if we do, for example, a whole brain analysis, trying to basically determine through the whole brain if we have some significant voxels, we may find ourselves finding none, because we are so conservative in our demands, basically, statistical demands. Okay? This also means that there is a difference in the threshold you get if you're using an ROI or some limited portion of the brain against the whole brain. Okay? So, and it's worth noticing. So you're allowed to do that. Just that your question or your assumption or your null hypothesis changes a bit, okay? Because one time I asked, where in the whole brain do I have something significant? And it will be harder to find. And the second time I asked, okay, I have some prior assumption that this part of the region is the relevant one, and I'm asking in that part which voxels are significant. It will be easier for me to find voxels there, but I'm limiting myself, so the question has changed a bit, right? I gain some and I lose some. So not a lot of times, most people don't use Bonferroni actually. Some people, what I usually do is use a false discovery rate, and again, without going into a lot of details, the intuition for the false discovery rate is that you select, okay, the threshold here means the proportion of the voxels that we found to be significant, the proportion of them that are significant by mistake out of those we found, and not out of the whole brain. So if before, when we just did, let's say, the whole brain or region of interest, doesn't matter, we had an alpha value, and that alpha represented our significance by chance, okay, through the whole whole matrix of voxels. Here we're talking about significant by chance from those we found active. Okay, so that means we have some adaptive algorithm here, adaptive methods, and the amount of how conservative this approach is depends on the number of voxels we found active. Okay, because it's a percentage of what we found active. Okay, so where there is little activation, we have something very conservative, and where there's and there's it's very conservative with less activation, and less conservative when we have more activation. And that actually makes sense, okay? Because well, I think it's better to see than to talk about it like with no examples. So I'll get back to the last point in a second. Let's see what we have here. Here we have some example, typical, this is, I guess, FFA. I don't remember. Maybe I have the exact contrast for this, but the idea is the same. We have some uncorrected data, okay? Uncorrected meaning I didn't apply any kind of statistical correction. So I've got a lot of type. I didn't correct for statistics, so.
False positives.
Yes, thank you.
Which is type 2?
Type 2, if I'm not mistaken. I'm always confused about it. I never remember it. Like in 10 years, I don't remember that. It's type. Yeah. What? The false positive one. That's what you should know. Okay, type 1 or type 2, it doesn't mean anything. But you get a lot of false positive. When you do the Bonferroni, okay, you might be missing. First of all the false positive are gone, or most of them, I guess. But you might lose some regions that may actually hold some significance. Okay, significant values. The QFDR, as you can hopefully see, is something in between in terms of what you get, and this is a very typical result. And again, it's because it's adaptive. So you can see, okay, sorry. You can see that you get in this, sorry, this is the uncorrected one. This is the QFDR, and you can see that you get rid of a lot of some of these guys, some of these clusters. They disappear, but the large cluster, they stay basically, well, not the same, but they stay there. Okay, here. Almost the same. And that's the adaptive part. So if you have something that is kind of widespread and robust, okay, with QFDR, with FDR system, you probably stay with it, and the small jittered clusters of signal of activation will probably disappear.
So FDR is only useful if you're having like a whole range of all voxels, not if you look at 10 comparisons or something like that.
I don't understand. What do you mean 10 comparisons?
If you compare 10 behavioral measures or something like that, you want to...
No, usually you do it, you apply it for within the GLM for voxel, for all voxels basically, to correct for the multiple comparisons between voxels. This is just an illustration from a model that we built in which we have signal and some noise, some random noise. Okay, this is just an illustration. Then you have this combined image, and the idea is to test which of these approaches or algorithms gives you the results that are most, well, let's say, most compatible with the true stimulus as it was modeled. And you can see the non-corrected one. So not surprisingly, we have we can see almost the whole signal. It's very hard to see now, but there's kind of a red circle around the real signal. Okay, and what's outside this red circle is the noise, and almost all signal is there, but a lot of noise is also there. Okay, doing the Bonferroni correction, you get something like that. So a lot of non-detection. Okay, the FDR, at least in this type of stimulus and noise, gives us the best. I would say it's not the best, but it's more adjusted or more in between result. Okay, covering quite a lot of the signal with not a lot of the noise, but again, there's a trade-off, okay? So you get more false alarm here, less false alarm here, but you also detect more, you have more true detection here and less here. So it's kind of adaptive. We'll see, we talked a bit more today about, for example, for MVPA, these things become less and less important, because sometimes what you do in MVPA, you get some responsive voxel, and you sort them by responsiveness, and then you decide, you analyze the most, I'd say, 100 most responsive or 200 most responsive voxels. Then the threshold doesn't mean a lot. I mean, you set some threshold beneath which you don't analyze because you consider it's noise, all right? But it doesn't really matter if when you set this threshold, you have there like 300 or 500 voxels, because usually you would take the first 100, let's say. Just want to have some kind of threshold. All right, so just to sum this up, we have the Bonferroni family-wise error. Usually when you do a whole brain analysis, you won't be using that. But you could at certain scenarios. For example, right now I have I'm doing this analysis, which I'm gonna feed this voxels value to a classifier, and I do it. One of the analyses is doing it in region of interest around the MT area, and I have for some subject very, very robust activation. Okay. So the idea again is, let's say I have there like, I don't know, 500 voxels, and I'm going to use about 100, 150, or 200. So then I can do, I can get either one of these corrections. It will, in this particular subject, it won't matter, all right? Because I will be choosing the, let's say, 200 most responsive voxels, right? So it will actually be better for me to do the Bonferroni because it's going to be easier for me to, the cluster will be isolated and more easy to see and to infer. But there are other ways. I'm just going to mention in one quick sentence the cluster size correction, which is very, very common and very, very useful. So the idea there is that there is some, and it's a true notion, that there is some dependency, spatial dependency between the voxels. Okay, so if one voxel is active, its neighbors tend to be active as well, to a certain point. Okay, and what you can do is you can get the results. Basically, again, you have a GLN, you get a t-value for each voxel. You get a map. You're not correcting it, but you do some kind of mathematical procedure in which you do some permutations. But the general idea and the intuition is to remove clusters that are too small. Okay, and you do that again in an iterative way. You do some permutation to check that you're not just removing or assigning values that are only true to this specific image that you have. So again, some kind of a different approach that assumes or builds on the fact that you have some kind of spatial relation in the activity of the voxels, and you're left with some cluster size that you determine, under which everything is gone, basically. So if it's 10 voxels or 15 voxels or whatever, you remove those patches and you are left with a significant cluster or clusters. Okay? Permutation test is also something you can do, basically quite similar. Let's not talk about it. Again, the details are not very important, but I want you to be aware of all these, because we're going to mention them also, and also that the general idea of trade-off between them. Okay, is that clear? Right? One gives you more type 1 errors, one gives you more type 2 errors. It really depends also on the question and analysis you want to do. Okay, now moving to the main talk of today. Start with multivoxel pattern analysis, and we have some things I want to cover this week, next week, and maybe even in the last class we have. But let's start with the basic. So, again, for some of you it will be completely new. Some of you probably heard some of it. So we'll start from the beginning. Usually, and today it's not only 3 millimeter, but 2 millimeter, but we have a standard size of voxels, okay? So 3 millimeter usually, but even 2 or even 1 today with, you have 7 Tesla. And what we talked about up until now is, let's say we define a region of interest, and then we have, make it simple, 2 conditions, and we want to see if this region is active more towards one condition than the other, or to one stimulus and not the other, okay? So what you get some estimate, again, using the GLN, or using any other way, you get an estimate of the signal, which each one of these voxels in the region of interest, you get some average, okay, and you get a value, basically, one value per condition per region, okay? It doesn't matter how you define this region. Well, almost 20 years ago already, people thought of the idea that this is maybe not the best, well, it's a good way to ask some questions, but not others, okay? And the idea is that there is some variability between each region, okay, within each region, sorry. It could be a large region, or it could be this small region of 3 by 3 voxels, okay? And the idea here, again, you see the red ones are very active, the yellow, and here it's white. Here it's not white, interesting. But yeah, this one is white on my computer. Anyway, they are less active. And again, the idea is that this specific combinatorics, the specific pattern of activation within a region or throughout several voxels has a meaning of its own, okay? And the idea, again, is that for each trial or for each stimulus or for each condition, it doesn't matter right now, you get a slightly different pattern. So it's this pattern for this space. It's like this, and this one is a bit different, but the average activity, for example, for all these activation profiles will be higher than this average in the FFA. Okay? So the FFA responds more. This is, let's say, this is the FFA, okay? So here in this example, they're both the same, but let's say we're talking about the FFA, and then this one will be darker than this one because the average activity is always higher than when you show houses to the FFA, and vice versa to the PPA, okay? But there is some kind of, that was interesting. There is information that we lose when we average these voxels, okay? Because the pattern is distinct for each one of these faces in this case, but it could be the same stimulus and a different condition or a different category of stimuli and so on. So that's the idea of MPPA. And again, now I do it voluntarily. I moved it voluntarily. The idea is like this. So again, you have some ROI. And if you have here these voxels, this is space, so these are voxels, and they are not organized now by the actual space in the place in the brain, but just put one next to each other in a vector, and this is time, okay? So if you have on black the average activity of this voxel, this set of this RI, this set of voxels, and on these blue and red, you have the two conditions, okay? Condition 1, condition 2. So it could be the case that this set of voxels, right, we're talking about space, so the set of voxels that you have corresponds in a certain pattern, okay? This one corresponds high, and this can't have low activation whenever you present the blue condition, but wherever you present the red condition, something else occurs. This voxel now is very active, and this one here is less active, but the total sum is always the same, okay? Or total sum or average is always the same. But the idea, again, if you take the profile of this activity, let's say it's the blue one, again, these are voxels, this is not time, so this voxel is active like that, this voxel is active like this, and so on. You get a totally different pattern here, the blue and the red, although, again, if you average it out, if you reduce this pattern into one single or two single values, you get something that is not significantly different. So that's the main motivation. Now, when we talked about functional organization last week, I raised this question, and I told you that, well, we get back to them from time to time. And these are kind of the question that people have been researching the last, I don't know, 20 years. They are not the only questions, but when we're talking about the visual system, on the cortical organization in general, we talk about how modular is it, how distributed are the representation. We talked about the resolutions, okay, and the effective resolution in which we can detect representations. We talk about large-scale mapping principles like centricity or object size, object viewpoints, things like that, and networks. And when MVPA comes into the picture, we continue to ask these questions, but we change the perspective a bit. And until MVPA, basically people ask, which areas are more active in a specific time point or condition, or in response to a certain stimulus. And now we switch the question into asking which areas hold relevant information, okay? And as we see, and as we continue our the next two meetings, once we find how distributed it, or how does the pattern looks like, okay, or if there is a pattern of voxel that represents bags and phones, mobile phones, I can see where it is and how it changes with the stimuli, and I can start to quantify my the model and recalibrate the model I have, and to see exactly how the representation in the brain, okay, how they correlate with our existing models or our behavioral models and such and such. That's what we have RSA for, but that's for next week. But the idea is we are now not only asking where or which parts of the brain are active when, but how can we understand better what is going on. So I'll start, today we'll talk about two things, about correlation and decoding. We'll start, we won't be finished, and next week we'll talk about the representational similarity analysis. So you're familiar with some of it, I know you're familiar with some of it. A bit, yeah, okay. Yeah, sometimes we know about it, or we just have the lingo, but not really understand what's the difference. But stop me if you have questions. The beginning, at least, it's very simple. Okay, so you know the main idea is, and it's try to understand some rules, okay, or some codes that are reflected in the pattern of activities that we see. So the correlation method basically, well, surprise, surprise, measures correlations, but more specifically, we want to see if these levels of correlation follow some kind of rules or categorization that we think that's happening there. Okay, so in this approach, we assume some kind of functionality or some kind of sensitivity to a category. That's why we choose our stimuli the way we choose them, okay? And then we want to see what happens with the correlation. And the basic idea is to check the correlation within the same category, so to see how these three exemplars, the activities, correlate between themselves, and these three, okay? We get some kind of a threshold or baseline level to see how the correlation is within category, and then we check the correlations between categories. Okay, we check how all of these guys correlate with the other category. And if the assumption is that if the within category similarity or correlation in this case is larger than between category similarity, that means that this region, and this is the where the information part at least comes in, it holds some kind of information about this category. Now, just from doing that, you don't know if. So let me rephrase that in a different way. So it means that, again, the representation of a certain set of stimuli is similar, is consistent. So it follows some rules that is somehow reflected in the constant activity in that brain region, okay? When we switch to a different category, this pattern changes, okay? So that means that there is some kind of information about the category there. But it's important to understand that just from this test, we don't know what kind of information. And we don't know two things. First of all, if this information, for example, in the case of visual categories, is it something that has to do with the semantics of the category, or something has to do with some common visual features of the category? We don't know that. And another thing we don't do, and this is very important to remember, especially when we talk about decoding later, we don't say that there is some kind of discriminability or some kind of, let's say, common activation pattern for one category and a different activation pattern for another category. Means that there's some information, yes, but it doesn't mean that this information is used in the brain in a certain way that we think about it, okay? Remember, you're kind of looking at the brain from the resolutions of voxels, okay? So there's a very, very big, discussion of how we can interpret this kind of information that we find there. So I think it's already fair to say that if I see some decoding in a certain region or some kind of correlation preference, I can say that this area participate or is relevant to that kind of category, that kind of representation, but saying exactly what it does or that the representation is there is it's kind of tricky to say. Okay, so correlations, I'm going to just go over a very, very classic experiment from Huxley, 2001. That's almost, 17 years ago. It's horrible, but that's life. And the idea is this. Again, this is the first time, it's not exactly the first time, but the first big impact the journal had on this discussion of modular or distributed representation in the visual cortex. And if you remember from last time, we talked about this Nancy Kenmusher and the FFA and how it was discovered, and then that later there was some kind of discovery or a journal that came out that said that FFA is not actually as modular as people thought it was. But then there was this paper was disputed. I showed you that as an example of circular analysis, but it was all part of this discussion about how modular the visual system is. And we also said that there has to be somewhere a limit to this modularity, even if we have some face region and place region, because we'll run out of real estate in the end, right? We can't have a region for every category we make up. So it's a small brain after all. It's not so small, but still, at least at the MRI resolution, that's the limit to what we say, and we can say something about faces that are very special, but there's a limit to computationally how you can achieve rich visual representation that we have. And this discussion between modularity and distributed representation continued, and it still continues today. And I also told you the spoiler that the truth is somewhere in the middle. But now we're going to cover this important example of that showing really distributed representation. And what they used 7 categories and some kind of scrambled images. And they presented them sequentially. And again, just the results. What they have here is the correlations, and we'll cover the details in a second, the correlation between and within categories. Okay, this is what you should look at. There's even runs and odd runs. I'll talk about it in a second. But the idea is, again, you have some brain activation, okay, and this is widely distributed, so you have some areas of PPA, FFA, and other lateral regions that you don't see in the slice. And if you, again, what you do is you divide the data to have 2 halves, okay, even runs and odd runs, and you simply correlate between the 2. Okay, this correlation could be from of the time courses, it could be on the betas, like in this case, it's the betas, or the t-values. The details don't matter really. But the idea is, again, if you correlate these images, basically you put all these voxels in a vector, one vector and one vector here, you correlate the vectors, and you get some level of correlation between 2 halves of the same category, and you get some level of correlation when you get, we use this data correlated to this data. Okay, so just from seeing these images, you can realize the amount of correlation between the blue and the orange, so it's not really surprising, but of course it was quantified. And what they showed this is just extended these to other categories. I want to jump to this. What they showed basically is very nicely that first of all, for each category, and I'm showing you only 2, but the others are the same. For each category, you get very high correlation when you correlate it with images from the same category, very low correlations when you correlate it with images from other categories, well, activations for images from other categories. What you can see here is two things. First of all, what I just showed you. Okay, this is the within, and these are all the between categories. But you can also, they did another thing, is that they removed to prove. Again, this was kind of an argument between modular and distributed representation. So we said, okay, let's the FFA is somewhere in there. Maybe most of the correlation we see is because of the FFA that is correlated. Okay, for two types of for two data sets of faces. So when this high correlation between faces, maybe what drives it is the voxels that are within the FFA. So they removed the FFA, okay, for this comparison, and what they got is this light colored, okay, the light colored bars, and they, for the PPA, for example, they removed the PPA voxels, okay, voxels that they found from a different localizer that are responsive to houses. And they found out, and that was the point, that even after removing these voxels that are classically face processing voxels or processing voxels, you still have a very high correlation between all other voxels in the region of interest, in the visual cortex. I don't remember exactly how they set what voxels are inside this analysis and whatnot. I think they used some kind of anatomical mask. They had several anatomical regions, but very, very widespread in the visual cortex. You can see something else here a bit. Can you tell me if you can see something else? There's some kind of, well, not oddity, but some kind of something you can think about. Yeah. So the cats have some similarity with faces. You can interpret it in several different ways. We talked about some global principles throughout the visual cortex, like animate, inanimate distinction. We'll talk about it again next week when we talk about RSA. But there are some reason you can think that there is some correlation between faces and cats. First of all, cats have faces. That's most cats have faces. They're both animate. You can think sometimes that you are, when you're looking at a cat, you usually look foveally at the cat. You don't see it somewhere there, at least when you focus on it. The size, the real size, real world size of these two objects are pretty much the same or similar. So there are several, again, talking about what's driving this correlation or the decoding. This could be semantics, but this could be also some kind of feature similarity at some kind of level. And like I said, in 1 minute I'll give you a 10-minute break, but like I said, this pattern of results was pretty much the same for all categories they used, okay? From chairs to shoes to whatever. All right. I think it's a good time to stop. So the idea is very clear, right? So we have, and this is what you usually do with correlation. You just check the within categories or within condition, within stimulus set correlation, some kind of baseline, and you check it with another. And the idea is that you have some kind of assumption here, okay? So they selected these categories because they expected to have, they could have found another result, of course. It doesn't mean that it works like that. But they have some kind of guess, educated guess, that you will be able to see a difference or higher correlation when people look at faces all the time or when people look at houses all the time, okay? And later we get to more data-driven approaches. All right, let's take 10 minutes. Peter, you want to write something else? You said?
Yeah, we have to look at my part.
Go about it.
Sure, the question.
All right, well, you will
Would it
remember.
be possible to maybe connect, I mean,
We have to
MacBook
think
you're using or
the important thing
laptop?
is the triggers from the MRI. See how they connect.
Yeah, but the thing with Windows is that for Chick Toolbox a lot of functions aren't supported by,
Yeah, I know.
at least officially.
Yeah, you told me that. I didn't work with Trade Toolbox for fMRI, so I don't.
Yeah,
But you work, so
no, but so they
specifically.
um, the Wiener lab basically works within the MacBook, but they have Windows desktop there as well, so they are going to try to run it on their Windows desktop there as well
Right.
to see whether it works the same. But if that doesn't work, it might be
Yeah, you have to come. You have to test it, and when you know that you need it, send me a mail.
Mhm.
I'll first ask Zara IT.
But it's not it's not a definite no yet at least.
No, it's not a definite no at all. I want you to, not a definite no at all. Just, for in your case, we'll need several things that will work together, so you need the trigger to, first of all, we need to see that everything physically connects. So you have USB, I think everything is with USB, also the triggers, I think it will be okay. I don't remember the connections that by heart, so, but let's say the physical connection are okay. If you want eye tracker also, which you might want, I guess, or not in the beginning, I don't know. But if you want eye tracker, we have to see that we have sync. So there are several things to. But
Right.
of course,
We can
in
try
general,
to-
yeah. In general, I don't see any problem. What we wanted to do first is to have really something just plug and play. That we have it already, like there.
For a MacBook in the lab or something like that, or
Yeah, no, or just we have all the connections already there, and just like ping, and that's it. But we don't have it yet.
I see.
So I think we have to go and we have to work a bit to make sure it's working. But there is no, from my side, there is no reason not to do it. Okay? It's just we have to see the trigger works, the screen works, and the eye tracker works.
And there is no because my computer is connected to the internet, but there is no chance that it can
No, you just get the inputs. That's
the
okay.
important why the Steambox computer is not connected to the internet is to make sure the timing there.
Well, it's two things. Yeah. So we want to make sure the timing is correct. For that, we remove the there's no antivirus.
So it's unprotected.
So that's why it's
So
not
the
connected.
antivirus would
Antivirus has some
timing.
kind of priority
Mhm.
thing with Windows. So we remove everything to keep it as light as possible. And because we remove the antivirus and firewall and everything, we put it out of the
But
internet.
then is there some kind of big firewall on the
Yeah, on the on the
connection between the two?
Yeah.
I see.
That's why you only get things through the other computers.
Right.
But with your computer, I mean, it's no problem.
If there's a virus on my computer, it will remain on my computer.
Yeah, yeah. The only thing you have to worry about is the timing, but I think it's okay. You can also, on your computer, it's no problem. You can dismantle the antivirus for that specific, drop the process for 2 hours. That's it.
Right.
So no problem. The only problem is to making sure that everything works. So first check with them.
Okay. Thanks.
I talked with Benedetta today.
Oh.
Yeah, so I hope this.
About the Helsinki blah blah blah.
Yeah,
Blah
I think
blah blah.
yeah, the blah 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 is moving forward, and hopefully they'll confirm everything in a couple of weeks. When do you want to? When was your plan? Like summer, sometime?
Yes. I'm not ready yet. So.
No, I'm not.
So it's not like
Yeah,
you know,
waiting to
panic.
that. Yeah, yeah, yeah.
So I'm not panicking or anything.
Do you have like the
So,
paradigm ready or?
the fMRI paradigm I do have ready, but
Okay.
I'm still struggling with the behavioral
Okay.
things that I want to do before.
Before
So
that.
I can't decide.
Uh,
You know, the more you read, the more questions
Yes,
you have.
yes, yeah. It's
And
better
then
not to read, not to write, not to.
No.
Less contact you have with the with the scientific community,
The better.
the simpler, huh?
Just never
Yeah.
ending.
I realize probably with your PhD also. When
No,
writing the
I
PhD,
couldn't stop writing my PhD.
I couldn't stop also, but also only after like writing the PhD, I realized how I should have done the PhD, basically.
I still don't know exactly.
Well, I know things that I should have done better. Probably they're not perfect, but it's clear. It's amazing how, yeah. And what's more amazing that
Terrible.
writing the discussion for the PhD, you have to read a lot, and I read so many papers that I have read before, and it was like reading them in the first time. It all goes. I don't. Yeah. Hopefully, there's some residual knowledge that stays in the brain, but yeah. Probably now, if I have to read it,
Hopefully,
yeah, hopefully, yeah.
But otherwise, it's a complete waste of time. I'm like, I could have gone to
Yeah.
a party or like, you know,
Yeah, I
with my
mean,
friends.
yeah. No. It's like it's amazing. Probably, if I have to read the same papers again, like now, 2 years after the PhD, it will be like the third time reading them for the first time. All right. Since we're a motivated little group, let's just continue, okay? And I want to run through the coding, and so we have a fresh start with representational similarity analysis next week. So like I said, one thing you can do is you can correlate the pattern, the activity patterns, and see if you have some meaningful differences in correlation. That will tell you, okay, I have some sensitivity towards this category and another. And I will just mention, we're talking about the visual domain here because that's the subject of the course, but you can do this basically for every kind of stimuli, or every kind of. So you can do this. We'll continue about the decoding now, and you can do this either correlation or decoding, as we will see in a moment. Not only for visual stimuli, but in general to all kind of different stimuli, tasks, mental states, and so on. And we're talking about decoding. We're talking about the ability to discriminate. Okay, the ability to discriminate between pattern of activation, and as a result, the ability to predict or to guess or to successfully guess a stimulus or a task condition from a pattern of activity. Okay, and this is like doing correlation, but in kind of a different way. So you're not only looking at the correlation, but you're looking at the other side of it, is how different, let's say, phases are for houses. And if I can find the rule, like the rules of correlation, if I can find the rules that dictate the difference, the underlying difference between these patterns and this set of patterns, if I'm giving a different stimulus, I can categorize the pattern, and from that deduce the stimulus that was presented. Okay? And by I mean the classifier that we train. So that's the idea. And to do that, we usually take a subset, a large subset, could be 90-80% of the data, to train the classifier. Okay, give the classifier exemplars. Okay, and these are tagged exemplars, so this is supervised learning. You give this pattern of activity, and you also give the assigned tag or the assigned stimulus. With enough exemplars, hopefully the classifier has made some kind of decision rule, and then you take some portion of the data that you left beside. You want these to be independent data, and you give this as an input for the classifier, and the classifier, if the classifier has generated a decision rule effectively, should say if this is a face, or a house. What was the question?
Yes, do you tell the classifier this is a space,
Yeah.
this is a house, or do you show
Yeah.
it the picture?
Oh, yeah, it's a good, it depends, but usually in this, like, classical example, you tell it it's a face or it's a house, so we tell it a condition, basically, okay? So we have two conditions, and we're going to talk about today on, I think, only two conditions. Maybe we have some other example that have, in this case, basically a 50% guess chance level, okay? If I guess it's 50% between these two, you could, theoretically, and people have done that, you could give a very limited set of stimuli, okay, and try to detect between to discriminate between the stimuli themselves. Again, you can do it by tagging, what usually people do. You categorize it. You can also try to create something that is closer to the actual visual features, okay? You can do that as well. It's more complicated. Usually we're talking about tags of categories. So, training trials and test trials. That's pretty simple. And again, can the algorithm correctly guess trials, identity, better than 50% chance? So, as we said, we have this pattern of activity, okay? And then we have some kind of space, multi-dimensional space. Each dimension is a voxel, okay? So, of course, to make it simple, we're always talking about two voxels when we explain the idea. And the idea of these axes is, if we take these 9 voxels, choose only 2 of them, we'll see them in a minute, and we take a pattern of activity. So this pattern of activity has some kind of level of activity in one voxel, and this is the level, and level of activity of a second voxel, and we place this kind of pattern in this space. So again, we simplify it, and we're talking about MVPA of 2 voxels, something that we never do, and we have more activity in voxel 2, I think. The yellow is more, if I'm not mistaken, and less in voxel 1. And we have the tag again, not the actual stimulus, but we tell them this is a house, right? So, yes, I was correct. So more activity in level 2, less activity in level 1. In the activity, the voxel domain, this is where we plot this specific pattern, okay? And we know that it's house, and it's a house, so we paint it red. Now we have a different voxel activity. It's the other way around. For this example, it represents face, so we're going to put it green, and we put it here. So more activity in voxel 1, less activity in voxel 2, and already we have 2 patterns in our space. Okay, so each of these dots is a pattern. Usually it's going to be 100 voxels, not only 2, okay? And if we collect enough data in this multi-dimensional space that we have of the voxels, we'll get clusters. Hopefully we'll get some clusters, okay? Unless we talk about noise or we talk about some kind of activity, some kind of, and this is exactly the information, okay? If we collect data from something irrelevant for this kind of a visual stimuli, we'll see some noise here, right? We won't see clustering. And the idea is that the algorithm, with this training data that we have, okay, first of all, like I said, some percentage of the training data we don't put here, we leave it to the test. But the training set that we are left with is being processed by the algorithm, and it should set some kind of optimal boundary. We'll talk a bit about the boundaries types in a few minutes. But the idea is, again, now I have the test, I've somehow managed to create some kind of boundary. As I have more exemplars, I can make this boundary more and more precise, okay? More and more resistant to false classification. But when I take this test back here, and again, I defined this clustering or this boundary without using them. That's very important because I don't want to sample the noise, the actual noise there, to overfit, and we'll talk about it again also in a couple of minutes. Now, these examples, the test examples of the patterns fall in this way on that space. And as you can see, from the previous section, so the bottom part is the red one, is the houses, and the top part is the faces, and 75% of the cases of the pattern were classified correctly, so these are houses and these are faces, and we have basically a 75% success of this classifier by the rule that the classifier has made from the examples that we gave it, okay? And because the chance level here is 50, so this is pretty decent classification level, okay? So by guessing, just guessing, with a 50% chance, now I have 75% detection, correct detection, so we're good. Okay, that's the basic. Now we'll talk about more about how we do this and what kind of insights people have shown regarding the visual system using these kind of methods. But this is the basic idea. Okay, we divide some kind of a portion of the brain. Again, this runs automatically. That's not good. But the idea is, again, you have some kind of problem with my computer, I guess, because we had it also before. Let's see if it stops now. Okay, no. All right. Let's go. Let's finish with that. So basically, this is exactly what I said before. So we have some kind of training tests, okay? Now we have not only 2 voxels, we have several voxels, n voxels, we have different level of activities. Wow. Yeah. It's kind of... No. 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 Yeah, no, it's not always, right? It's selected slides, so it's very strange. We have this kind of training vectors, okay? These are the different level of activation, so this is more active than this voxel, so on. So we have some commonalities for the bottles in this case, you can see, and some commonalities in the pattern of activation for shoes in this case. We can generate some kind of rule. We put this boundary, and now we give this example, which is pretty similar to the other shoes. So probably the algorithm will place it in the right position or the right part of this space it generated, and recognize it because it's in the blue part. Recognize it in the correct way as a shoe. Also for this one, and some kind of activity patterns that are less similar to one of the categories that we use for training. This is kind of less typical. Probably not probably, but they might end in a miscategorization. So this shoe, okay, something that was recognized as a shoe will be recognized as a bottle, and vice versa. Now, let's go to some actual data about concerning visual domain. So this is a work from 2003 already, and what you see here again is this different kind of categories. And you can see here, this is not time again, this is voxel number. What you see here is a different pattern, again, multivariate pattern, okay? So high activity in this voxel, low activity in that voxel. We have, I think, 10 categories here. And this is, again, just to, what they showed here is sensitivity to categories. But what I want to focus on is just highlight the difference or the added level of analysis we get from the multi-voxel patterns. So, if we take, for example, we have, again, for simplification, 2 voxels, okay, and we have 2 conditions. And one voxel is active in one condition and not active in the other. and the other voxel just the opposite thing, the opposite pattern. So the average activity, okay, could be similar, okay, in both, well, this is voxel 1, this is voxel 2, but in both conditions will be similar. So the average of the blues is basically identical to the average of the reds, okay, because there was, let's say, if we have 1 and 0, 1 was active and 1 is not active, so we have 1 and 0 and we average them, and then we have 0 and 1 and we average them. So that's pretty clear. What we also want to find, if we have some kind of representation that activates both voxels in both conditions, but in a slightly different way. So in this case, it's a bit different. The black ones are the baselines. Okay. So in this case, this voxel is active only in the blue and this only in the red condition. Here they're both active above baseline for the blue and the red conditions. So the voxels are very responsive. But when you contrast condition 1 and condition 2 directly, again, you won't find any kind of difference. Okay? Because you collect the average, in univariate, not talking about MVP, a univariate, you average the activity here and here. So although if you average the activity in the whole region in one condition, let's say the blue condition, you average these two blues and compare it to baseline, you see some activity, of course. If you average the red and compare it to baseline, you see some activity. If you average the red and the blue and compare between them, you will see none. No difference, okay? So again, the inspecting the pattern in a multivariate way helps you detect subtle changes or suddenly some patterns that look the same or activity that look the same in two different conditions. You understand that it's made the same by the averaging of two different subsets of voxel in each condition, each one of the conditions. Now, if you so if you have the voxel space that we talked about before, okay, you try to set some kind of a boundary, decision boundary, to select between the two categories. Let's say houses and faces. Okay. You can also train a nonlinear classifier. Okay, or in other words, you can try to find some kind of more sophisticated, more complex rule that is not linear in this space. Okay. This rule will enable you to detect, again, consistent or some very, well, maybe informative boundaries that are not detected in a linear way. However, they hold some problems. Well, let me say a few words on that. Let me first move here. Okay. Let me see how I'm going to explain this. All right. First, let's keep that for a minute. I'll get back to it in 2 slides. But keep in mind for now that interpreting such kind of rule is less straightforward. Okay? So if I have, for example, only 2 categories, and I know that one is more active, well, when one, let's say I have 2 categories and 2 voxels, again, make it simple, so one voxel is more active in this category when this category presents, and the other one is less active. Okay? And if this is consistent, I have some kind of boundary, I can interpret or say something intelligent about these voxels, okay? That this voxel or set of voxels contributes to this kind of pattern of activity together with that set of voxels. When I have some kind of complex behavior, it's less easy to interpret. So how come this voxel, for example, is active more in, let's say, this, when I present this blue category, let's say it's faces, okay? How come this voxel is more active in this sub group of phases, okay, but less active in most phases. Right? So it might give you a more accurate reflection of the activity, but something that you have less to work with, right? You have it's very hard to interpret and say something intelligent. It might be the case that you can, but usually it's harder to say something intelligent about this kind of behavior, okay? I want to understand if I have some straightforward relationship between the activity of the voxels and some assumption that I made, for example, about the different categories that are represented there, okay? If I know that one voxel is consistently active here or consistently active there, that makes sense. Well, it makes more sense, or it's easier to refer it to other models or other scientific assumptions that you have. But we have also technical considerations that make us prefer these linear kind of classifiers. So first of all, just the results of this paper, really the details are unimportant here, but you can see a couple of things. So what they check, the ability to discriminate between, and generalize again, between the given set of stimuli, okay? And they check this selectivity in free voxel selection, i.e. the whole brain, or just object selective region, excluding, for example, the early visual cortex. So first of all, what you have to notice here that the chance level is very low. The actual chance level, that is because we have 10 categories, okay? So the chance level is 10%. So everything significantly or way above 10% is already like a great success. So so all of these results are highly successful, right? You can see that the linear classifier, the linear support vector machine, is always better than the poly one, okay, the more flexible one. LDC is another algorithm that I'm not going to talk about too much because usually it's far, far less effective. What people usually use and what you should use, unless you have a very specific reason not to use it, is linear support vector machine, okay? And I want to say a few words about why linear support vector machines. But before that, there is a big difference here between this graph, the top left, and the top right. Care to explain what is the difference and why do you see the difference? So first of all, they are both significant or both very successful. So here we have around 80% success or discrimination, and here you have about 50. Why is that, you think? So this is all voxels, all visual voxels, and this is only LOC. Any guess?
Because it can only discriminate objects.
Right?
Theoretically at least.
And
not the gaps from the phases.
yeah, so somehow related to that. So part of the, I would say yes. But more specifically, if you in this type of experiment, this kind of stimuli that they used, I guess some of the success, this phenomenal success really of this classifier was dependent also on low-level features, I guess. Some commonalities, some local contrast, okay, that contributed to this, and that are not equally represented or equally maintained in the representation in LOC. Okay, so if a representation in LOC, we know that the resolution there is less, right? It's like more it's large receptive field. You're not talking about the same kind of representation here and there. And then again, it depends on the, I don't know, on voxel size that you have, okay, on the eccentricity of the stimuli you have, on the, well, the commonalities of differences in local contrast, local features. within your stimulus set, so it depends on a lot of things. But again, you have some kind of, this is first, by the way, this is very, very like impressive classification rate, right? It's 10%, it's chance level, this is around 50, it's very, very impressive. It's still not as impressive as the other one because you have, I guess, more information there. But going back to the algorithm that you use, and I want to stress out there are many different algorithms that people have tried, and from what I know about the last, I read a few articles also this week about it, nothing new there. What people usually use is the support vector machine. Support vector machine, the linear support vector machine, which yields the best results. Now, we're not going to go into why that is exactly, only about the linear part, okay? So the first thing you got to know that this one is what you usually see and what you're usually going to use, and why linear? So we said one thing, and that is that linear, that nonlinear rules, let's say, are harder to interpret. Okay, we know that it's less straightforward to understand what a nonlinear behavior of a voxel within the space means. Actually, how does voxel act in reference to our condition or our category? Okay. And this is just from a paper that tested these 6 different classifiers back in 8 years ago. But there, like I said, there are numerous works like this. So that's one reason, the inability to understand exactly or in a less straightforward way what we see. But the other one, which is very important, is the tendency of the nonlinear classifier to overfit the data. When we talk about overfitting the data, we talked about this, I think, in a week ago, 2 weeks ago, on a different subject. What I mean by overfitting the data in this context is, again, overfitting the data basically means that you let the specific noise contribution of your specific data dictate the result you have, or in this case, the rule you generate. Okay? So with overfitting, if I have think of it intuitively, if you have a very flexible rule, okay, with a lot of degrees of freedom, you can really make really great boundary that really fits your data well. Okay, you have maybe 90% success, but you'll take into account the specific contribution of noise into your data set. Okay, and then your generalization ability will be pretty much, it will suck. Okay, so again, if just to make it, because this is important, I think you got it, but still, just paint it a bit. If you have these guys and the x's, right? And let's see if I got it correctly. So if I have some boundary, some linear boundary, I will have some mismatches here and there, but I will have something that generalizes to a new set of stimuli or a new set of experiments pretty well. Okay, because most of the new data will follow this rough division. If I have something very flexible, non-linear, okay, I can have, I would say, that boundary, right, or something like that. I get all the x's here correctly, but for new data sets, I'll probably have a pretty lousy detection rate or a discrimination rate, because these specific changes are partly caused by the specific noise I have in my data set. Okay, this is also why the reason why you train a subset portion of the data and test with a different portion of the data. Okay, so this is the main reason why you don't want to use non-linear classifiers. And this, just as a final note, this in fMRI, this is a specifically kind of a hard problem because of the relative amount of features or voxels relative to the samples that we have. So usually when people talked about classifiers, we talked about, I don't know, 4 dimensions, let's say. We have to have 4 dimensions that you model the space with, and maybe you have 1,000 repetitions, thousands of examples to create a rule. Okay? In MRI, sometimes you have, let's say, 100 voxels. So these 2-dimensional space in which you put the rule into, it's like 100 dimensions, okay? And relatively, you don't have that much exemplars. Sometimes you have beta values. The betas are, let's say, and you average, let's say, 5 repetitions of the stimulus, okay? And you have 1 beta, and then you have maybe, I don't know, 20 betas. You have a low repetition rate. So the ratio between the dimensions and the samples is really not in your favor in MRI. And this, again, can cause more overfitting. So, again, in MRI, you use the support vector machine and the linear one. All right. Enough technicalities. But are we good up until now? Okay. So, again, the basic idea is very intuitively straightforward. Now let's try to talk about an example of 2 in the visual domain. And I think that will be enough for today. So I'm going to talk about 2 papers from the lab of Frank Tong. One deals with the representation of orientation tuning in the visual cortex, and another more with memory. So in this first example, which is a pretty complicated article, but I'm going to give you the gist of it. People were presented with, there were 8 actual orientations, okay? The task, if I'm not mistaken, was just fixating at the center and reporting when the fixation changes color or something like that, not related to the orientation. The idea, again, was try to decode from the brain activity in early visual cortex what kind of orientation was presented. Okay, to see if there's orientation information. By the way, to check if there was orientation, if it was orientation information and not just, I don't know, some kind of pixel-to-pixel information, they jittered the phase here sometimes a bit. Okay, so sometimes in some trials this path was black, this one was white, and then another try it moved a bit. Okay, and because you remained in fixation, it means that not every when you collapsed all the basically when you trained, you didn't collapse, but when you train examples of 45 degrees, it wasn't exactly the same 45 degrees pattern on the retina. They were all 45 degrees, but the phase was a bit different from trial to trial. Okay, so the exact pixel to pixel mapping wasn't the same. So that was not what the classifier was trained on. And this, if I'm not mistaken, again, this specific research, they didn't create beta values. They just used the activation, the percent signal change. So if you have a trial, and the trial was, if I'm again, I hope I have this right, but I think it was 16 seconds of flashing, let's say 45 degrees orientation, okay? Then you take something like that, let's say, or this part of activation, okay? You reduce it to 1 value, okay? Sometimes the integral of this activation part, okay? You have 1 value. And you have this kind of profile. Let's say this is for 45, and for 135, let's say something like this. Okay, so you have a different kind of value for each condition. Okay, so it's not beta, it's just raw signal. And the idea was like this. We know from neurons that we have some tuning curves, okay? We have preferred tuning of orientation in the some V1, V2 neurons. And the idea is that this preference would be translated to voxels in a way of some kind of small, really small but random preference. Okay, so we have around a million neurons in each voxel. We have subset of neurons, and one subset will be randomly larger than the other. So the total activation of this kind of neuron, okay, of not neuron, of voxel, will be, let's say, towards 135 or 20 degrees and so on. All right? So what you see here are the voxels. They're not, they don't look 3 by 3, but they're, I don't know, 3 by 3 or 2 by 2. The voxels are, they're spread out on the flat surface of the cortex. Actually, it looks like they're smaller, right? I need to check the details, but it doesn't matter. So what you have here is voxels on the flat cortical surface. That's why they look distorted, and each color represents a slight preference for one of these orientations. And again, the idea is it's randomly because of the local different distribution of local subpopulation. Okay? To see it more clearly, let's say in a single voxel, this is voxel number 50, you have slight preference for this kind of orientation. Again, because of the specific population of neurons you have there. Okay? In voxel, this voxel number 100, you have a slight preference for this, and so on. Their assumption was, or what they tested is that you could create a really significant tuning curve from some kind of linear combination of the voxels you have. So if you have 200 voxels in V1 or V2, or you pull them together, doesn't matter, they did all these tests. If you have this kind of readout models, okay, you can, again, if you assign some kind of weight to the connections that connect each kind of model. So let's say this model, 45 degrees, is connected to all voxels in this region, but the weight, okay, the weight structure is different for this unit and for this unit. And this is what they did. So they created this weight structure, and the algorithm changed the weight composition or weight structure in such a way that it will maximize the preference for a single orientation. Okay, so I did it according to real data. So I got the stimulus there. I get some kind of pattern information. Okay, so one voxel is more active, one voxel is less active. I know the tag of the trial. I know it's a 45 degrees tag. And I have this vector now that corresponds to 45 degrees. Now I change the weights in that way that now the 45 degrees detector or model will have maximum activity. Sorry. Okay. So if in this trial that now corresponds to 45 degrees, this voxel was less active, I reduce the weight here, but I raise the weight here. Same I do for 135 and each one of the other 8 orientation that I have. And okay, and they actually were able to create these preference or tuning curves, so-called tuning curves for these units. Okay, so that's, I think, very impressive. So first of all, yeah.
So they basically try to model some kind of pooling
Yes.
mechanism or something like that?
Yes.
Of a theoretical area that's monitoring everything.
Yes. Yeah. The idea is can we read out from a population of voxels some kind of is the population of voxel, and does the population of voxel encode orientation? Is that information of orientation is somewhere hidden there in the combined activity of V1 neurons or V2 neurons? Okay? you have a combined activity. Again, yeah, they're assuming a readout. They're assuming two things here. So they're assuming the information is there, but can it be utilized by a readout, some kind of readout unit that has some kind of reinforcement mechanism? Okay, so this is, yeah, they assume that. I mean, they can say you can say something less than that. You can say only that there is some kind of information there. Okay, but here they actually go and suggest, at least test a biological plausible model that if you do that in a very specific way with changing the weight here, you actually can read out these preferences for orientation, and this is very, again, like I said, very plausible biologically. Okay, we know that this is how neuron, in general, how they work, and it's very makes sense that this is how it's done. But did I answer a question or? Okay. All right. Let's. We have a couple more minutes. So again, I want to say that this, first of all, is an example how you use some classification on not on betas or estimates, but on the actual signal, percent signal change. And I think it's a nice, first of all, it says something about again, we're talking about the visual system. This is somehow something that really talks about the way some information is, like I said, encoding in a very large scale. Well, it's not large scale. It's read out in a large scale or combinatoric or population vector sense by pulling together, again, local variations. Okay, so in specificity for a certain domain, in this case orientation, into sharpened representation by a high-level detector that incorporates this whole population information. And again, it's very biologically plausible because each, and this is shown, so each voxel here again is assuming to have several subpopulation of neurons with preferential to a certain orientation, as we know we have in the V1, V2, okay, and it shows that these kind of local variations can be pulled together, okay, even in the resolution level of the voxels. Okay, it doesn't mean that the actual readout units parcel the V1 to voxels, right? It just means that information could be there. Well, it is there and could be used. Sorry. Okay, and this is again, like I said before, it's very hard. It's very important to say that information is there, and in this case can be used. So the combinatorics of this activity can be used or can be read out. It doesn't mean that it's being used or read out in the resolution that we are talking about. Okay, we arbitrarily divide the area to 400 voxel, to 200 voxel, to 100 voxel at a certain resolution, and I do need to check later the actual resolution of these voxels. But let's get to the results of this. So understand what they did more or less. And this is the decoding of orientation. Okay, so they actually. Okay, so what? Let me go a step back. So what we did is we talked about how to train the algorithm, basically to train these detectors. Okay, by assigning different weights. So again, I get a pattern of activation. I get a tag. Let's say it's a 45 degrees grading. Okay, I have this pattern of activation. I want to maximize the activity in the 45 degrees model, so I assign weight to the 45 degrees. I'll do that, I don't know, 1,000 times or however times I can do it. Okay, and then I basically train some detectors. I train the detectors by changing the weights. Now I give a new pattern. If I train the detectors right, okay, so this new pattern should highly activate the correct detector. If I give a new pattern, a new sample of, let's say, 135 degrees, if I succeeded in training the classifier, then the network will activate and the maximal power or maximal activity will converge in the node of the 135 degrees, because that's how the weights directed the activation. And this is what they found. So what they found here is on the black, you see the actual stimulus, okay? And this is averaged over, I don't know, this is subject one, no, this is only one subject, but averaged about all the trials that were, let's say, horizontal trials. And you can see for all, I think, for all kind of orientations, for all 8 orientations, you can see that most of the decisions, basically the decisions that go out was along this orientation. Okay, you can see also that there is some kind of deviation, but to closer orientation. Okay, so it's very, in other words, on very high percentage, the classifier, which had basically 8 outputs, 8 optional outputs, chose their correct output for a given new set of activations, new activation, new set of boxes. Okay, this is just summing the whole for each subject. This is aligning all different orientation like this. So this is the total deviation, total accuracy for all orientation for one subject. So again, you can see that these 3 subjects were quite well. This one performed a bit worse, but it was still quite impressive. And this is just, they did some other tests and checked, changed training days to see how robust. And this was, again, training on one day and then waiting 31 days or waiting 40 days and testing. And this is just, I think, a control they had to show that it's robust. And I'll show you the last, yeah, I think it will be the last for today. Last manipulation, which will bring us to the last point. I want to talk about decoding, and we'll complete the talk next week at the beginning. And what they did here is they wanted to see the role of attention, or in other words, also see the role of attention and also understand the nature of, a bit more the nature of the representation they were able to decode from V1 and V2. So they had a training task in which people just passively saw a 45 or 135 degrees grading, okay? And they had this is just training. This is just looking at the center, okay, and seeing this 45 either black or white, or 135 either black and white. This was the training set, okay? You get these responses. And then what they do in the testing set, they show this pattern, okay? And now you had following a cue to attend to either the black, the 45, or the task was the 45 on the 135, these guys or these guys, okay? And the black and white were counterbalanced, so you can ignore them. They were divided equally among the test, basically all kind of conditions you have. So the task was attend to the 45 or to the 135 degrees, okay? And what they found was kind of impressive. So they found, again, wider shoulders for this graph. I don't remember the quantification exactly, but more or less They could decode what the person was attended to at in each given basically trial. So again, they collected some data, trained the system to differentiate between 45 and 135 visual stimuli. Then you have the tagging here, so you tell in one trial person, focus on the 45 degrees, and you know that's tagged at 45 degrees, but you don't tell that to the classifier, just give the activation in V1 or V2 or V3 or V4, okay, or all of them together, and the classifier has a 50% chance of saying the correct tag. And in most cases, I don't have the percentage here, but in most cases, we're able to identify correctly the attended stimulus. So, first of all, this is just the difference between the four. This is for the subject, and this is the four areas. I think it's less important. What's important here is that, first of all, for the visual aspect, is that you see some kind of attention modulation, okay, that could be detected by the difference, basically by the trained classifier. So you can think about it. I'm not sure what the answer is actually, but it makes you think, how does attention drive the activation in these kind of in these voxels? Okay, so if we had some kind of training, okay, on 135 out of 45, so it was able to deduce some kind of rule. Okay, there were some similarities or correlations within each orientation that weren't there between the orientation. That's how you can differentiate between two. Now the attention, okay, the visual attention could be somehow recreated this differentiation, okay, got one representation, let's say the 45 representation, different enough from the 135 representation that was basically there, right, because the stimulus includes both of them. But somehow it differentiated one presentation from another in such a way that the classifier that was trained on either of them or both of them could use this information it gained here to differentiate between the attended and unattended stimulus. So I'm leaving this to you as a thought. Maybe we'll talk about it in the beginning of next week. I'll think about it also. The other thing I wanted to say in this context is that we see here some cross-trial trap decoding. Okay, we'll continue from this next week, but just as again food for thought. Up until now, we use some kind of we use the data, divided them, let's say, to odd or even, or we left some portion of the data. We had some kind of a bunch of stimuli. We trained them, and then we use some kind of the other part of the data to generally test our rule. But now we have different, well, in this case, different task condition, different state of mind, different action that was done by the subject here. Okay, so the training test had something qualitatively different than the training set. Okay, one time you saw it, you saw one of the two orientation, and the other one, in the other case, you saw both of them, but you had to attend to one of them. And the fact that you can generalize from one to the other enables you to, like I said a minute ago, at least think about or deduce some really deep understanding about perceptual or cognitive processes, in our case perceptual. So we'll continue from there, and we'll talk more about next week about the way you can either generalize between different set of stimuli, different tasks, different mental states, and from that deduce principles of perceptual processes.